When an ice cube melts, the process is endothermic. It absorbs heat from the surroundings. When a fire burns, the process is exothermic. It releases heat into the surroundings. Endothermic means heat flows in, exothermic means heat flows out. In an exothermic energy diagram, the products are at a lower energy level than the reactants. The vertical drop is the enthalpy change, which is negative. The hump at the start is the activation energy, the barrier that must be overcome. In an endothermic diagram, the products are higher than the reactants. The enthalpy change is positive because energy is absorbed. Activation energy is always the initial barrier, while enthalpy change is the overall difference. Enthalpy change can be calculated in 4 ways. 1. Hess's law. 2. Standard enthalpies of formation. 3. Bond enthalpies. 4. Calorimetry. First, Hess's law. Imagine 3 different paths. Path A is direct. Path B has 2 steps. And path C has 3 steps. No matter which path you take, the overall delta H is the same. This is why enthalpy is a state function. So basically, you just sum up the enthalpy changes of each step to get the overall enthalpy of the reaction. Now, let's look at the combustion of methane. CH4 plus 2O2 gives carbon dioxide plus 2 water. The formation enthalpy of methane is negative 74.8. For carbon dioxide, it's negative 393.5. For water in the liquid phase, negative 285.8. Oxygen is in its reference form, so 0. Using the formula, sum of products minus sum of reactants, we can calculate the, you guessed it, enthalpy. And we finally get the enthalpy of the combustion of methane. The enthalpy change of a reaction can also be estimated using bond energies. Breaking bonds requires energy, while forming bonds releases energy. The net change is bonds broken minus bonds formed. First, let's draw the Lewis dot diagrams for each molecule. Using tabulated bond enthalpy values and applying the formula, we get negative 818. For the same reaction, the heats of formation method gave us negative 890. When hydrogen gas reacts with chlorine gas to form hydrogen chloride, 1 hydrogen-hydrogen bond and 1 chlorine-chlorine bond are broken. 2 hydrogen-chlorine bonds are formed. Breaking the bonds requires about 679 kilojoules, while forming new bonds releases about 862 kilojoules. The net result is negative 183 kilojoules. At the particle level, heat transfer always goes from hot to cold. Red particles represent hot, fast-moving molecules, and blue particles represent cold, slow-moving molecules. When they interact, energy flows until they reach the same speed and temperature. At equilibrium, they appear purple and no net heat flows. In a coffee cup calorimeter, a hot metal cube is placed into cool water. Heat flows from the metal to the water until they reach the same temperature. The change in the water's temperature is measured with a thermometer. The heat transfer is calculated with the equation Q equals m times C times delta T. Specific heat is the energy required to raise 1 gram of a substance by 1 degree. Here, the hot metal is the system, and the water is the surroundings. Heat lost by the system equals heat gained by the surroundings. Both reach equilibrium at the same temperature, showing conservation of energy. A heating curve shows how a substance's temperature changes as heat is added. Sloped regions represent temperature increases within a single phase, where heat raises the kinetic energy of particles. Flat plateaus occur during phase changes, such as melting and boiling, where added heat breaks intermolecular forces rather than raising the temperature.